We all know that the atmosphere convects, and wind is a very obvious example of that. And you probably think it convects because wind flows from high pressure areas to low pressure areas. And if you think that, you're right. But why are some areas in the atmosphere high pressure and others low pressure? And the reason is buoyancy. So in low pressure areas, the air is hot and moist and it's light, and so it rises. In high pressure areas, the air is dry and it's dense, so it sinks. So it's buoyancy that causes those pressure differences. And when you think about natural processes and you go back to the root cause, it's invariably buoyancy. And buoyancy drives convection in fluids, and it also drives convection in the mantle. It drives magmas out of the mantle, and that's what I want to talk about. So let's start with a very simple case of convection between a hot and cold plate. And you've probably seen examples of that. Your stove is a good example of convection in a fluid. So let's take a fluid between a cold plate and a hot plate. The hot plate at the bottom of the fluid heats a boundary layer above a boundary layer at the bottom of the fluid, and in heating that fluid, it makes it light, so that fluid starts to rise. At the top of the tank, below the cold plate, the fluid loses heat to the cold plate and it becomes dense and it starts to sink. And those buoyancy differences between the bottom and the top are what drive convection. And those buoyancy differences can be very small, but they still drive convection. And more or less the same thing happens in the mantle, with one fundamental difference that I'll come to. The surface of the Earth is cold. It's about 20 degrees on average. The centre of the Earth is the core, the iron-nickel core, and that's 1,000 degrees hotter than the mantle above it. So the core acts as a hot plate. It heats the boundary layer immediately above the core, and that's about 100 kilometres thick. It makes it light, and that layer starts to rise, and it starts to rise in the form of mantle plumes. The cold boundary layer at the top becomes denser as it cools, and it starts to sink back into the mantle at subduction zones. There's a fundamental difference between the fluid between a cold and a hot plate and the mantle, and that fundamental difference is that the upper boundary layer is cold and stiff, so it can't flow back into the mantle in the form of negative plumes. It flows back as a stiff body, and those stiff bodies are called plates. What drives magmas out of the mantle? And the question again, or the answer again, is buoyancy. The mantle has a density of 3,300 kilograms per metre cubed, whereas basalt has a density of 2,850 kilograms per metre cubed. So the density difference is 450 kilograms per metre cubed. If that magma is 10 kilometres below the base of the crust, then that density difference is applied over a depth of 10 kilometres. And that gives you a pressure of 4.5 by 10 to the 6 kilograms per metre squared. So there's a huge pressure on that magma, and that pressure drives the magma out of the mantle. But that pressure is caused by the buoyancy difference, or the density difference, between the magma and the mantle.